Hello, everybody. So this time, I'm sorry, I'm going to be a little low tech. You won't see my face, although that might be an improvement actually, but never mind. So I'm currently traveling and I thought I had everything ready, but it looks like my laptop is not the best for doing this type of thing, and therefore I will just limit myself to speaking and going over these slides. So what I want to do is present a few models. So before the break, we looked at a variety of problems linked to environmentally transmitted pathogens. And now I'm going to present a few models. So I think this lecture will be roughly half of the content for this week. I will have to tape another lecture later on, which will be more focused on actually running simulations and so on, and presenting a few additional models. But I want here to give you an introduction to the type of models that you would see when you're considering environmentally transmitted pathogens, because there are some very interesting specificities in this type of models. So what I'm going to do is I'm going to, for part of the lecture, I'm going to go back to a few models that have been around for quite some time, but are not necessarily well known, but that will serve as a good illustration of what it is that goes into these models. And then, so I'm going to present a few models, like a model of, by someone whose name I'm probably going to slaughter, Shetanovic. I'm not entirely sure how that beginning is said, which, well, I'll come back to this. Then I'll present a very simple model for environmentally transmitted pathogens by Capasso, but that encapsulates some of the interesting ideas that we will see throughout these lectures. Then I will show you a little model for the zoonotic transmission of a waterborne disease. By zoonotic, I mean that it will involve actually both humans and an animal species. And finally, I'm going to spend a little time talking about schistosomiasis, because there are quite a few models that have been presented, formulated about schistosomiasis, and there's actually way more that I'm going to present here, and I might expand this in the future lecture, in the next lecture. But okay, without any delay, let's get into that first type of models. So I will point out, in principle, this should be clickable. Yes, it is. So there's a large collection of models, actually, by Shetanovic and a few others that are, I should say, I discovered recently when I was preparing this course. I did not know these models before. They sort of fell into oblivion, almost, we should say, although they have some very, very interesting characteristics. And Shetanovic is someone who was working in the 70s up to the 90s. I'm not entirely sure what period exactly, but someone who was in the former Yugoslavia and was working for WHO as well. And there's quite a few interesting ideas in there. And I'll point out this second model, a second paper from Briscoe in 1980, that actually is the way that I made sort of connection with the Shetanovic models. But he also mentions a few other models. And I just want to point out, yes, these are more than 40 years old now, some of these models, but they have some very interesting characteristics. And you have to understand, I think it's important to see that um, we keep on reinventing the wheel, and you will see that the models here they incorporate quite a lot of interesting ideas. I will point out as well that those models of Chetanovic, they're in discrete time, which is a type of model that I haven't covered yet. And I think the next lecture will take this and develop a bit more. So these are interesting models in a way, and I will very briefly explain when we get there. And they're also very detailed on the epi side. Okay, so they incorporate quite a lot of important processes. So the first one that I want to show you is a model for tetanus. So tetanus is a bacterial infection. It's called by a bacterium called Clostridium tetani, or tetani, it depends where you are from. And what's important with tetanus is it's the prototypical environmentally transmitted pathogens because it's everywhere. So there's spores everywhere in the environment, there's in the soil, in the dust, in manure. And what happens is that those spores develop into bacteria when they enter the body. They are not spread person to person. So they're just present in the environment. So if it's, as I said, I mean, there's no feedback from contaminated people. These bacteria are just there. And so if you are thinking about how to model this, it's going to be quite different from anything else we look at. Typically, there's an incubation period, which is between 3 days and 3 weeks, the average being 8 days. Actually, depending on the severity of the wound that inputs the bacterium into your body, the incubation period can vary quite wildly. But most cases occur within 2 weeks. It is quite a bad disease. Essentially 1 or 2 out of 10 cases are fatal, which is a bad number. Now, it is a vaccine preventable disease. And so this is, for example, the CDC. Again, I'm doing this inversion of colors, which I could have removed here because I'm not superimposing myself on these slides, but never mind. So this is an inverted color version of the CDC poster in terms of vaccination. So you can see that there's a number of vaccinations that happen when you are a kid. Then preteens get another vaccination, and then typically the recommendations vary country by country. I know I'm currently in France, actually, and that's where I come from. And now in France, unless you're over 60, the boosters are every 20 years, not 10, like it says here on the CDC website. So that's something that varies a bit. But anyway, it's vaccine preventable. And actually, the model that Chetanovic is looking at incorporates vaccination. So here, it's not in this basic model, but when I detail this model in the next lecture, you will see how things work with vaccination here. So I hope you can see my pointer. So there's 2 types of susceptible. There's the newborn and the regular susceptible. So newborns are up to a certain number of months only, after which they move into the susceptible population, the general susceptible population. Upon infection, a newborn is incubating and then sick, and likewise upon infection, a regular susceptible becomes incubating and then sick. When you're sick, you can recover fully, so go back to the susceptible population, or if you're a sick newborn, if you recover, then you're not a newborn anymore and you just recover as a susceptible. But you can also, die from tetanus, which moves you into this compartment, the tetanus death. Or if you recover, you can have active immunity. Most people will have some immunity. And in this model, he considers that immunity is 10 years. Then the newborns also can have some passive immunity if it's transmitted by the mother. And that passive immunity doesn't last very long. It lasts about 6 months, and after that, you go back into the susceptible population. So as I said, what I will do is in the next lecture, I will show you the model. I didn't think it was worth spending the time explaining that type of model here. But what I want to emphasize, even if I don't get into details, is that this type of model is interesting because you will see that what you parameterize the model with are not rates the same way as we've seen and we will see in a few slides for ordinary differential equations. When you have a discrete time model like this one, what you do is you parameterize by the survival in a compartment, or the rate of transfer from one, and it's not a, I mean, it's a rate, but it's a proportion of individuals who transfer from one compartment to the other. Okay, so as I said, we'll come back to that in the next lecture. The model, if we look at it from a mathematical point of view, from a model point of view, is summarized this way. And as I said, we'll come back to that next time. Another model that Cvetanovic looked at was a model for cholera. And so I'm going to briefly detail it here. Again, as I was pointing out before, Cvetanovic's models are very detailed. And I should point out that they're a bit, it's interesting. This is, I mean, looking at these models, I realized that things have moved away from the type of work that Cvetanovic was doing. And it seems like now with COVID, we're back in a situation where this is going to happen again. But what was important in Cvetanovic's models is that they are all of these models you will see are published by the WHO. They're part of the bulletin of the WHO or other publications. So clearly these were used for planning purposes, which is not the case so much anymore with more recent models. But here there was really a sort of group that was providing modeling to the WHO directly. So because these models are meant to be used really for planning purposes, then that's why they are so detailed. And you can see here the model for cholera that he's suggesting is a precise example of this. You can see that people are newborn, then they become susceptible. They can be contact carriers, they can be incubating infectious, incubating non-infectious. When they are infectious, after their incubation period, they'll become sick, infectious, they can die, they can be healthy resistant, they can be convalescent carriers, and after a while, either they move, if they are convalescent carriers, they can move from being that to being healthy resistant or chronic carriers. And all of these compartments will contribute differently to the contamination of the environment. Okay. Again, as I was pointing out, this is a very different type of formulation, and I want to spend the time in the next lecture to explain really how these things work. So for now, I'm not going to go into more detail, but I just wanted to highlight this type of very detailed model. Now, what we're going to look at now is a model by Vincenzo Capasso, who's in Italy, and who's done some who is still doing some very interesting work in epidemiology. I believe that in my intro lecture, way back at the beginning of this course, I mentioned that there was a book by Capasso that I really liked, and it's from the 80s, so he's been around for quite some time and has a very interesting look at models. So the model that he looks at is a very minimalistic model, I would say, but it incorporates what we really want to see in an environmentally transmitted pathogen model. So it's a model that very simply looks at the human population, and that H here is the fraction or the number, depending on the cases. Here I'll show you numbers, but the number of individuals who are bearing whatever pathogen you're thinking of. Okay, so that model, I think the underlying idea is to look at cholera, but it could be for any pathogen that's transmitted by the environment. And I think it's worth explaining because that model, even though it is super simple, it already incorporates some very important ideas. So H on the left here is the human population, and it's not only the human population. So we suppose there's a total number of N, capital N, humans, and the H here is how many of these humans are actually carrying the agent, the infectious agent, so the bacterium or the parasite or whatever that you're interested in. Then E is the load of pathogens in the environment. So E is environment, H is the human population. And what you can see is that there's a loop, but I will try to edit these slides eventually. Here, this is not a proper flow. Likewise, going from E to H, it's not a proper flow, it's just showing the effect. And that's going to be very important here. So before I detail this a little bit, the parameters, let me explain. So DE here is the inverse of the average lifetime of an agent, of a pathogen agent in the environment. So that rate of movement out of E is simply saying how fast are pathogens evacuated from the environment because of their death. Here, the same way humans can recover. So gamma H is the rate of recovery from the infection. So 1 over gamma H is the average time you spend infectious. And then there's these two important components here. So CHH is how much movement, how much humans who are contaminated by the pathogen are infecting the environment. Okay, so imagine, in the introduction lecture, I was talking about the fecal oral route, or you could think of peeing, whichever way your pathogen of interest has to go from the human it is colonizing to the environment. And so here we assume this is a linear, okay, it's a per capita rate of movement. But it is not, I shouldn't say a per capita rate of movement, it's a per capita rate of creation. Okay, and GE is the growth rate of the pathogen in the environment. And it's essentially the force of infection. So it tells you how much infection of humans results from the number of pathogens that are in the environment. And as I said, and I'll come back to that in a second in the next slide, it is important here to note that these are not flows in the way that we saw in the beginning lecture, the first lecture altogether in this class, and that you saw in other models in the other courses. Okay. So before we get there, let's look at what the incidence function looks like. So we write it as a product. So the incidence function is a product of the probability for an exposed susceptible to get the infection and how many individuals are exposed. Well, we compute that by taking this product n beta p, where n is the total human population, beta is the fraction of those humans that are susceptible, okay, because a certain number of humans might be resistant, and p is the fraction of all of those that are exposed to a contaminated environment per unit time. And I quite like the way Capasso writes it. He says it's the probability per unit time to have a snack of contaminated food. Okay, so essentially you are drinking the water or you are consuming food that is infected by the bacterium or a parasite. So this is that P is how many, what's the fraction of those exposed that are actually doing this. Okay. Typically, the assumption is going to be that P and beta, they're independent of how many pathogens are in the environment and how many humans are contaminated. Okay, this is assuming, of course, you could make this more complicated if someone is aware that there is a cholera outbreak, for example, then they might be more cautious in their use of water. So that would reduce P. But as a first approximation, he assumes that P and beta are independent of what is present. And the other assumption is that the function H is a saturating function of the number of pathogens present in the environment. And I'll come back to that in a second. So next course, I'm going to show you some numerics about this model and of the other models. But in the meantime, I'll just show you what you can write mathematically in this case to ensure that you have a saturating function. So here you would assume something like what is written here. You're assuming that essentially if there are the function is increasing. Okay, this is this first condition here is simply saying that if there are two numbers of pathogens, two concentrations of pathogen in the environment that are ordered this way, then the growth function is ordered in the same way. Okay, if there is no pathogen, there is no growth and contamination. Okay, in the absence of pathogen, you cannot be contaminated. The second derivative of the incidence function is negative. This means that the function is concave down. Okay, there is it's like an upside down parabola, not necessarily parabola, an upside down hyperbola. Okay, it will limit to some quantity that is positive, but it's not going to increase further. There's no change of concavity in the function, for example. Finally, well, two very technical assumptions. This is just saying that the first derivative, the right derivative, okay, so if you take the derivative of the function and that function might not be, it's typically not defined for negative numbers, but when you evaluate the derivative at 0, this is a positive quantity, and it's also not, it's a finite positive quantity. That means the curve at 0 of g, the incidence function, is essentially initially increasing. Okay. And finally, we want that the limit when the argument goes to infinity of the incidence divided by the value of E, okay, because remember this is E, essentially, is less than this quantity that we write here. Okay, as I said, these two assumptions, they're mathematical in nature. You don't really need to think about them specifically. When I illustrate through numerics later, you will see some examples of functions that satisfy these requirements. Now, the model looks like this. If we take all of this into account, we have a differential equation for the number of pathogens present in the environment and a differential equation for the number of humans contaminated. So what's important here, compared to other models we have seen, this is not a model where we make individuals flow from one compartment to another. Now that's a very important distinction from what we did before. In a classic epidemic model, for example, I have my S individuals and my I individuals. Well, there's a flow from S to I, and when there's a flow from S to I, what we do is we take individuals away from S and move them to I. And likewise, if I have an SIS model, if I have individuals who are in I can move them back into the S compartment. Here, this is not the case. So you can see that, for instance, this CHH that is coming in positively here is not removed from the H equation. And likewise, this DEE here is not added to the H equation, because what is important is that these are different types of individuals. So you can't, for example, say that a human transforms into a pathogen, but the flows are proportional to the number of humans, for example. Okay, so this is a very important distinction, and you will see that for virtually all models of environmentally transmitted pathogens. So this CH here, well, yes, there's a loss here, but that loss, for instance, let me look at the two equations. So H prime is saying there's a growth, essentially due to incidence, of the number of infected humans, and that growth is dependent on how many environmental how many pathogens there are in the environment. But then the number of humans infected also decreases because of recovery. Likewise, the number of pathogens in the environment is a linear function of the number of humans who are infected. So the more humans are infected, the faster the growth of the number of pathogens in the environment. And the negative term here is not one that goes into H, it's one that just says these pathogens in the environment, they die after some time. Okay, so they are removed from the pool of pathogens in the environment. So this is really important. Okay. So this is what I write here. E prime does not have a minus G, and H prime doesn't have a minus CH. That was what I was just explaining. Now, this is a very simple model. What does it do? Well, we can compute an R0, a reproduction number, essentially, for the model. So it has this slightly weird shape compared to what you've seen before. It takes the form of the ratio between the product of the incidence function, the derivative of the incidence function at 0, multiplied by how fast humans are contaminating, okay, divided by the 1 over dE is the mean lifetime of the pathogens, and 1 over gamma H is the mean duration of the infectious stage of humans. Okay. And then there is this result, which is very classic, on the other hand. If R0 is between 0 and 1, then what we find is that there's only a trivial equilibrium. And by trivial, we mean it's 0. Okay, so the two components E and H are both 0. And that equilibrium is globally asymptotically stable. So if this R0 is less than 1, both the number of humans infected and the number of pathogens in the environment go to 0. On the other hand, if R0 is larger than 1, then we have two equilibria, 0, 0 as before, but that one is unstable, and a positive equilibrium, E star, H star, that has both components positive, and that one is globally asymptotically stable unless you start at 0, 0. Okay. So in view of this, this model is very much like the model that we saw before. I will point out right now, and I will come back to this in the next lecture, that when you integrate, when you solve numerically this problem, you very quickly run into problems. The problems are linked to the sizes. To have, essentially, you're going to have to make some hypotheses about the parameters in order for the model to make sense. Because I was taking random parameters, essentially, and I was ending with more infectious humans than my total population of humans. I will come back to that when we do that in the next lecture. Now, one other thing that Capasso did in the same paper was to look at the effect of a periodic component, because that's quite important here. Here he says he takes P. Remember, P is the fraction of people that take a meal. The people that are potentially exposed and that take a meal or drink a glass of water, whatever. And here he's assuming that, well, instead of being a constant, that number could be a periodic function. So that would, for instance, apply if you are looking at a component that is seasonal. You could say, well, for instance, if you're thinking of environmentally transmitted pathogens in food, that could be, well, at one point in the year there is salad, and at another point in the year there's no salad. And the pathogen gets on the salad when you wash it, and so if there's no salad, you're less likely to have it. That type of idea. So in that case, what he does is he looks at the incidence as being of this form. So like before, except that we now call it H of E, but we multiply by a P of T, so this is a periodic function. And then we define two quantities, which is the minimum of the value of P of T over one period and the maximum of the value of P over one period. One of the technical hypotheses that I didn't want to get into now becomes of this form. Okay, so there's a P max involved in here, not just P. Then you can define an R0 minimum and an R0 maximum in a way. And the difference between the two is that they use a minimum and maximum value of P. And then you have the following result. That second one I need to check, because he writes that this number should be less than 1. I am not entirely sure. I think it should be bigger than 1, but I will confirm this next time when we do the simulations. So what we have is, as indicated, if our 0 max is between 0 and 1, then the model always goes to extinction. So the disease-free equilibrium is globally stable. But if this condition is satisfied, I think, as I said, then there's a unique, non-trivial, periodic endemic state. Okay, so we have a periodic forcing of a function. What we observe as an output is something that is also periodic. Okay, so now I want to spend a little time talking about a more recent model by Walters, Hamilton, Sidhu, and Dunbar. So it is a model that has been used in their case to model Giardia transmission from possums to humans. So let me show you how this one works. And this one is much more classic. But again, you see a bit the same idea as we just saw in Capasso. So the idea is that we have an animal species that's transmitting between itself. And the model is a bit unclear, I should point out, as to what they really mean by transmitting between themselves. I think they are still thinking of a fecal-oral route transmission, but they're thinking about transmission between animals of the same species and between humans. And the most important thing then is the coupling. Okay. So the susceptible and infectious animals, there's animal-to-animal transmission, recovery. So these are SIS models. Likewise for humans, there's susceptible humans, infectious humans, there's transmission and recovery. But additionally to that, there is a deposit rate from the infectious animals into the water, so of either oocysts or cysts. So like we saw in the Capasso model, so the pathogen is in the water. There is a death rate of the pathogen in the water because it can't survive for all time. But then there's also a pickup rate by humans, by susceptible humans, and that leads to the transmission of infection. Okay. So the model looks something like this. It's two SIS models where the transmission is really, I should have written beta SAIA, but what's important here is this term. Okay, so you can see the environment, the water is contaminated. W stands for water. Water is contaminated. Exactly like we saw in Capasso, the rate of contamination here is alpha IA, and then there's a rate at which humans uptake the contaminated water, and that leads to transmission. But there's also potential for transmission directly from human to human and animal to animal. So the model looks something like this. So this is a mass action term here, recovery, mass action here, and what you can see is that then W increases this way. This is because of animals depositing in the environment. And then there's an uptake by, so this W SH plus IH is simply saying how much uptake by humans there are. Okay. And this is the death of pathogens in the water. And for humans, now there's human to human transmission. And I should point out, if, for example, you're considering a disease where there's no human to human transmission, you would just set this beta H to 0. Okay. This is still quite a generic model. So you see the environment gets contaminated and it comes into the human population to contribute to the infection. But there's also human-to-human transmission of the disease. Okay. And this is the recovery. So essentially what they do is they exploit the fact that the total population of humans and animals is assumed to be constant, and therefore they simplify this model and they write it in a way that there's only 3 equations. Okay. So this is the equation for the infectious animals, the infectious humans, and the water. They find 3 equilibria. One is the disease-free. I mean, for this particular model here. Okay, so remember that we've removed SA and I and SH because we say we know what they are. And so the disease-free in this case has no infected animals, water, or humans. There's also an endemic model, an endemic equilibrium, which interestingly, well, because of the way this is formulated, there's an endemic where the disease is endemic in humans but absent in animals. Okay. And finally, there's one where there's endemic levels of the pathogens in both humans and animals. So, as we've seen several times now, what you do is then you compute an R0. The R0 is very simple here. There's an R0 for animals and an R0 for humans. But you can see that already the situation is a bit more complicated than many of the models we have seen so far. We have that the disease-free equilibrium, where both I's and W are 0, is locally stable if R0A and R0H are less than 1, and it's unstable if any of the 2 is greater than 1. Okay, so it is stable. Stability requires both to be less than 1, but instability requires only one of the 2 to be less than 1. Now, if the R0 for humans is greater than 1 and the R0 for animals is less than 1, then what we get is that endemicity only in humans. And finally, interestingly, the one that has both A and H positive requires R0A, so the R0 for animals, to be greater than 1, and R0H to be less than 1. And I'll point out that if you read the paper, they say all solutions go there, but from a mathematical point of view, if this is what you're interested in, the proof is not global. So it's not entirely clear that all solutions go there. I thought this was an interesting model to present. And to finish, I don't want to add text. To finish, let me take a look at a few models of schistosomiasis. So the first model by Woolhouse is, you can find it in this paper. Actually, the 3 models, or 2 of the models, are in this paper. This is, I recommend, it's worth a read. It's as you can see, it's a long paper, and it reviews a lot of different models, not only his, but a few models by a few different authors. And it's really worth a read. There's a second one about control measures, and there's a variety of papers from the early 90s by Woolhouse about this. So let's look at this model. By the way, I should point out that in some instances, if you read the original papers, for example, the Capasso paper that I was showing you earlier, you will notice that I have changed the notation. Typically, I have tried to keep the same parameter names as they have used in their papers, but I have often changed the name of the state variables because I like to be sort of consistent with my state variables. So that's what I've done. Okay, and this is precisely a case here. This is not the same notation as in Mulhouse, but it's the same idea. The idea is the following. So remember, schistosomiasis is transmitted by snails. People pee in the water if they're infected. This infects the snails, who in turn release what are called cercaria that penetrate your body and infect you in turn, etc. It's a parasite that has quite an interesting life cycle. So the model is the following. So first, he assumes that there are capital H individuals and that all these individuals use a body of water that contains N snails. And he denotes, or I'll denote, but he sort of considers the mean number of schistosomes per person, and that's going to be denoted little, so lowercase, because it's the well, I should have used a capital actually here, but never mind. I'll edit the slides, by the way. When I'm back in Winnipeg, you'll get much better slides and videos. So IH is the mean number of schistosome per person, and little is the proportion of patent infections in snails. So this is the prevalence. The prevalence of by patent infection, he means snails that are actually infectious. Okay. So the model is very simple. So we have that the variation of the number of schistosomes per humans is alpha times the number of snails times the proportion of snails that have a patent infection. Okay, so again, I'll sort of stress this. There's no, I mean, this is at the level of the person, and you can see that we're not multiplying by IH here. So this is sort of a characteristic of all these environmentally transmitted pathogen models, is that the contamination, the rate at which things happen, is quite different sometimes from the way it's done for regular models where you have person-to-person contamination. Okay, so we have the number of schistosomes per person increases this way, and you can see the alpha here is the number of schistosomes produced per person per infected snail per unit time. Okay. And the number of schistosomes per person diminishes by the average life expectancy of a schistosome. Okay. And now the proportion of infections of patent infections in snails increases based on a transmission parameter, the number of humans times the mean number of schistosomes per human. So H times IH is essentially how many schistosomes there are in all the human population that's attending that water body. And 1 minus IS is, of course, S. Okay, so this is the number SIS, because the sum IS plus SS is equal to 1. So this is simply the product of IH times SS. Okay, I'm not using the variable S sub S because it's not required, because it's a proportion. Okay, and finally there's this rate mu2, where 1 over mu2 is the average life expectancy of an infected snail. Okay. So you can see how this model articulates. There's the new, the number of schistosomes per people evolves this way and is diminished by when the schistosomes actually die. And the number of pattern infection in snails evolves this way. Now, he defines a basic reproductive rate, and that rate, so this is a two-species system, and it's always complicated when you're thinking about several species to think about how a reproduction number works. So here, what you have is the reproduction number for schistosomes. So essentially, it's one loop. So how do you go from a schistosome to a schistosome? So you get it this way. It's the product of alpha times the number of snails times beta times the number of humans that are using the water body, divided by gamma times mu2. And the behavior of this model is very classic. We have an equilibrium without disease. Okay, this is the disease-free equilibrium. There's no humans bearing schistosomes, where there's no mean number. The mean number of schistosomes per human is 0, and the mean, and the proportion of snails bearing the schistosome is 0. And that number, that equilibrium point, is locally asymptotically stable when this number R0 is less than 1, and it's unstable when R0 is bigger than 1. And then there's another equilibrium, which can be computed in terms of 1 over R0, so 1 minus 1 over R0. And of course, you can see that this quantity, if R0 is less than 1, this quantity is negative. Okay, so that means this equilibrium only exists in a biological relevant sense. Okay, it exists all the time, but it's biologically relevant only when R0 is greater than 1. And when that is the case, it is locally stable. So the situation is very classic. We have a disease-free equilibrium, which is locally asymptotically stable when the basic reproduction number for schistosomes is less than 1. And when that basic reproduction number for schistosomes becomes larger than 1, the second equilibrium, the endemic equilibrium, comes into the positive quadrant. Okay, it becomes positive in both components, and it is then locally asymptotically stable. Okay, so the paper of Woolhouse, as I was saying, is very rich in models. There's a variety of models in there that you can look at. I really recommend taking a look. But one that I'll just quickly illustrate is when you introduce latency. So usually before, between the time a snail is infected and the time when it becomes, when it starts to release the cell carrier, there's a period, and that is called the pre-patent or latent period. And so what he does here is introduce this latent period. So you can see that I'm still considering humans exactly the same way as I did before. The infection of humans is the same, but it's using IS, and now instead of just IS as I had before, I'm introducing an LS for latent, and that latent is produced at the same rate as before. Okay, this 1 minus LS minus IS, again, now I'm assuming that there's susceptible snails, latent snails, and infectious snails. So 1 minus those two is susceptible snails. So the same number as I had before, but now there's a rate of movement from LS into IS. Okay, so 1 over sigma is therefore the duration, the average duration of a pre-patent period, and there's a depth of Cercariae, a depth of snails here. The rest is the same. And so if you compute, for example, this here is the fraction of infected snails that survive the pre-patent period. Okay. And it's used here to compute the basic reproductive number for schistosomes. So instead of, as it was before, we add this F here, which is how many snails, or the proportion of snails that survive the pre-patent period. In this case, we also have an endemic equilibrium. I am not writing the LS because it's not really interesting, but the IH and IS that we had before become a bit more complicated, but they can still easily be computed. And like we had before, when when R0 is larger than 1, this equilibrium is locally stable. Okay, and as I said, there's plenty of models. So if you read the same paper, you'll see there's models where infectiousness of snails is lost, which apparently sometimes happens. Because most of the time, I mean, those models, they consider that the snails are infected and they remain infected for their entire life. But it seems that sometimes some snails might lose infectiousness and still be alive. So that's there's a model for that. There's a model with larval population dynamics. There's models where he has simplified things so that you can summarize everything in a single equation. There's models where human immigration and emigration take place. There's models with reservoir hosts, etc. I mean, as I said, it's quite a long paper. It's worth a read. I'm going to talk about another model of Woolhouse. I think it's in another paper. I need to make sure where my reference is. I'll go dig it out. Now, this is an interesting one because one of the things I do a lot is what I'll call metapopulation models, and this is a type of metapopulation model that is very interesting. So here he considers the number of schistosomes in a given person. Okay, so we have a person and we label each person. So you can see I'm going to write I sub I, the number of schistosomes in person I. So here, for example, in this graph, I have 3 individuals, I1, I2, I3, and I1, I2, and I3 are the number of schistosomes that each one of them has. So instead of considering a mean number of schistosomes in humans, I'm considering individuals, humans, as separate entities, each one of them, and I'm counting how many schistosomes each one of them has. And then there's a certain number of sites, okay, L of them. For simplicity, he assumes that all the sites have the same number of snails. Okay, so each site has n snails. Then here I have 2 sites, and IS1 and IS2 is the mean number, the proportion of infected snails in site 1 and site 2. And the idea is that some individuals might make exclusive use of one site. Okay, I1 and I3 here are using respectively S1 and S2, but some individuals might move between sites. Okay, and that's actually, I have to say, I didn't know this model. I like it quite a lot because it is I have done this type of thing for malaria, for example. But for malaria, it's difficult to think of mosquitoes as acting in a single place. Okay, whereas here, what's really nice is that the sites do get infected, so it is possible to have this great heterogeneity and to actually say each individual is going to one site or another. So I will spend some time in the next lecture showing you how to simulate this, for instance. So the way you describe the model is the following. So it's very similar to before, but now if you're looking at an individual, for example, I is how many snails, how many schistosomes there are in individual I. Well, that comes from their attending that individual, each of the different sites that they're going to. Okay, so this here, this eta ij is the rate of water contact by individual I at site j. Okay, so this is saying individual I goes to all the sites j from 1 to L. So they might not go to all the sites. So if they don't go to a given site, so suppose that individual 1, well, if you take this one, this case here, individual 1 goes to site 1, but not to site 2. So that means that eta 1, 2 is 0 in this case, okay? Eta 1, 1 has some value, positive value, while eta I 1, 2 is 0. Eta 2, 1 and eta 2, 2 are positive, and eta 3, 1 is 0 because there's no individual 3 doesn't go here, but he goes here, so eta 3, 2 is positive. Okay, so you see the idea. So the load that an individual carries depends on their visit to the different sites and how many snails that are infected are present in each of these sites. Okay, and then they evacuate some of the schistosomes at this rate gamma. Okay. Likewise, for sites, what we have is the same way, but here you see we're summing on I. So this is for site J. So J is 1 to L. For a given site J, how many infected snails there are depends on the visits of infected individuals, and the eta ij's are the same here, okay, because they were before. They indicate whether a given individual goes to a given site or not, and the rest is the same. Okay, and I will detail this better in the simulation part of the talk that I will do next time. And last model that I wanted to show you is a bit the same in terms of, let's say, complexity, but takes a different approach. So here, this is a model that was published by Tweet, Tien, Eisenberg, Earn, Ma, and Fitzman. So except for Tien and Eisenberg, everybody here is from Canada. And it's about the cholera epidemic in Haiti in 2010. And what they looked at is a model that looks like this. So the idea was that in Haiti, there was this cholera outbreak in 2010. And one of the things is that there's a river that can carry cholera through part of the country. There's also people that move between places and so on. So here they are looking at what's called a proper, it's a metapopulation model. So this is a model where you see these big boxes. These big boxes represent a location. In this case, it was the equivalent of provinces in Haiti, which are probably départements because it's French speaking. So it's département in Haiti. There's 10 of them, if I remember. And so what they have is they have an SIR model for humans. In this case, it's only humans, okay? They have an SIR model. It's cholera, so the water gets contaminated. But what's interesting here is that they have spatial interactions. So let me first explain the model itself. So let's look at the bottom one, which is a simple model, and then I'll explain the spatial aspects. So the index Q here refers to the current department, the current location. Okay, so the index here, P, is another location, so I have locations P and Q here. So this is an SIR model, like you know. Okay, so there's a force of infection, lambda Q. It's multiplied by the number of, here it's, I've used little letters, so these are proportion of susceptibles, infectious, and recovered. Okay. Typically I use lowercase letter for proportions and uppercase letters for numbers. So here this is the proportion of susceptible individuals, infectious individual, infectious and infected individuals, and recovered in, we typically call these locations patches. Okay, so this is patch Q, this is patch P. Okay, so this is a very standard model. And except that it is an environmentally transmitted model, so what happens here is that the infected individuals produce pathogens in the water. So they excrete the Vibria cholera in the water, and the water becomes contaminated. That water contamination exits after a while. Okay, so the pathogens cannot survive indefinitely in the water, but it is through the water that the individuals are infected. So this lambda Q here, typically, I mean, it could involve transmission human to human, but typically this is absent. So you could imagine that most of the transmission, if not in all of the transmission, is coming along this path here. Okay, so I have my water contamination and it acts on the susceptible population. Now let's look at the coupling. So I've detailed only in this patch. I should detail in both patches, but never mind. So here I've put, this is the classic transition, but here I've sort of illustrated this lambda SQ. I've made it a special state because that's where the crux of the model is. So what goes into the contamination of susceptible individuals here? Well, several components. The water, okay, the local water, so if they're using local water, there can be, although as I said, this arrow will typically be shut off, okay, there could be direct transmission of some sort. I mean, this is a model. It costs nothing to put this arrow and then say it's not there. Okay, so there could be a direct transmission of some sort, but what's important is there's not only transmission from the local water source, there's also transmission from remote water sources, and that transmission can happen because of two factors. They can what can happen is an individual from this patch here, patch Q, could travel to patch P and contaminate the water there because they're contaminated with the water. Or you could be, for instance, downstream, patch P could be downstream from patch Q, and contaminated water flows from patch Q to patch P. Okay, so the way they incorporate this is what I would call not a true metapopulation. I mean, it's a true metapopulation, but it's a metapopulation with implicit movement. So what they do is that they say that the rate at which this should be multiplied by IQ here, the rate at which IQ goes into this is this product here, kappa times P sub p, p sub q, d to the n. So let me quickly explain what these are. So d, first of all, is the distance between regions. Kappa is some coefficient, okay, some constant, never mind it, it's just something that allows you to scale things, etc. P, capital P sub p is the population in P, and capital P sub q is the population in Q. So P, 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 Q over dn is actually what we call a gravity term. It mimics the way gravity operates. So if you have two bodies that are interacting, they generate a force which is the product of the masses of the bodies divided by typically the square, but of the distance between them. But here they put an n because they allow for other weights. I mean, typically, if you're thinking pure gravity, that would be d squared, but it could be d cubed if you wanted to say that d was more important, etc. Okay, less important. Sorry. But anyway, so you see how this happens. So there is an implicit coupling between the locations. So it's not the same as the Woolhouse model that we had before, where people were, but I mean, it's the same type of idea. So in the Woolhouse model, people explicitly go to the different places, although they explicitly interact with them. Here, this is an implicit association, but it's another good way of representing things. Okay. So the model looks something like this for all p's from 1 to however many patches you have. You have a equation for the susceptible, the proportion of susceptibles. Okay. One remark. They typically in their simulations they assume that mu, the birth rate and death rates, are 0. So they just consider a model where the population doesn't increase or decrease. So this is a classic SIR model, okay, with this water contamination term. And the force of infection is that thing we were seeing before, okay? So force of infection includes contamination by humans directly. So if that's present, or you could biff it out if you don't assume that there is any type of direct contamination between humans, then contamination of humans from interacting with contaminated water, and then these long distance effect, okay, that involve this term here, where you have a gravity. So as I said, this is a gravity type term, and that theta is the influence of how much prevalence of cholera you have in the other locations. Okay, and that prevalence, the effect diminishes with distance. Okay. And what they do is, this is from their paper, they do a lot of numerical simulations. I think this is the result of 1,000 simulations. And they look at, this is the date, and these are the locations, okay? The different departments in IT. And you can see how the infection spreads. So from dark blue, low prevalence, to lighter color, more to the red, representing higher prevalence or incidence. I don't remember what they're showing, but yeah, here is the same. Okay, and you can see, so this is a spatial look at the propagation, because you can see, for example, it starts here and actually peaks here, and then it moves as time progresses to a variety of locations, and it gets to different locations at different times. And that's it for this lecture. As I said, the next lecture will have some numerical aspects of this. I'm preparing a few simulations to show you. I might talk about a few more models. I'm still preparing this, and I'm afraid, same as this one, it might be a day or two late. That's it.